So for this week, just to give an outline of what I'm hoping to do, we'll review some of the aspects of polarization of light that we had talked about last week. I will probably consign some of these other topics in polarization to a little video because, for example, the boundary conditions and Fresnel coefficients, you need to know how to use the Fresnel coefficients, but you won't have to derive them in this class. But I think you should see the derivation once. So I'll put it into a video and you should learn how to, I recommend you watch it and at least understand how they are derived once. And then we will use them in the course, or you will be expected to use them in some of your problems and so on. And then these two other topics, I think of them as sort of interesting because it tells you how we make many of the wave plates and polarizers that are in use in your lab, for example. So, and also one of the topics, which is optical activity or chirality, you kind of explored that last class with the sugar solution,
Yes.
So both of those topics, the physics behind them, sort of the material science, so to speak, or how that material prepares a different polarization state is an interesting thing for you to know, but it's not something, again, that usually we do a lot of problems on or that we have to worry about from like, a theoretical perspective of like how we actually make those materials, for example, or something like that.
Well, here the what is the expression for chirality? Yeah, we did.
Here, what it means, chirality, is that left-handed and right-handed circular polarization have different refractive indices. So that, but it also there. I will talk about that when we get to that.
Yeah. Okay. It is so.
Or it's circular birefringence, but then optical activity is one step further beyond that.
Okay.
Yeah. So just to summarize again, mostly we will focus in the class on the first aspect and understanding how to use polarizers and wave plates and understand how to predict the polarization state when you go through a wave plate. That's a very critical thing for you to know so that you understand how to use them both in the lab and in problems that you'll be doing. And as I said, these other things are supplementary things that you should see at least once, probably in an optics class. So I'll put them into videos. You can watch them. And then we'll try to move on to the aspect of the interference, which is the lab also for this week. And it has to do with how waves form superpositions in spatial domain, how you can create superposition of waves that extend over space and what that looks like in the lab as well. Okay. So, you guys are able to see clearly with all the lights on? Yeah, it's fine. Okay. So just to quickly review, in the last class, we talked about polarization. Remember that for electromagnetic wave, in addition to say the wavelength, which governs the K, 2 pi over lambda, and frequency, which is omega 2 pi f. And in addition, we also have the amplitudes, E0 x and E0 y, along the x and y directions, meaning that we are taking into account the vector nature of the light. Okay. And in addition to these amplitudes potentially being different, even the phase between the x and y components could be different. Of course, notice I've only chosen x and y because the electromagnetic wave is always transverse to the direction of propagation, z. Because here I chose the direction of propagation along z, so the electric field always has to be in the xy plane in that case. And we talked about all the different states of light, which I'll quickly review. And then we discussed, for example, with linear polarized light, when epsilon equal to 0 or epsilon equal to pi, epsilon equal to 0, the electric field lies in a line along the first and the third quadrant. And at the angle of this line is given by the ratio of the components, E0y over E0x equals the tangent of the angle that it makes with respect to the x component, x axis. Similarly, here, and the same formula is valid, but now epsilon equals pi means that the line lies along the second and fourth quadrant. And we also talked about how if you build a polarizer, for example, I gave you an example of how one can build a polarizer with wire grid for microwaves, or for optical frequencies, we use things like plastics, which have polarite molecules. Those polymer molecules are arranged in such a way as to only allow one axis of light, one polarization of light to pass through. And that is denoted by the transmission axis in this figure over here. And if you take two such polarizers and change the angle relative between them, then the intensity of the light that comes out follows what is called as Malus's law. That's just because the angle made by this, so the light coming out of this polarizer is oriented along the transmission axis, but when it hits this polarizer, that makes an angle with respect to the transmission axis. So the the state of the light that's coming out is at an angle with respect to the y-axis, and the amount of the light that's transmitted, or the amount of electric field that's transmitted, is the component along that transmission axis, which is E naught cosine theta. So the square of that gives you I naught cosine squared theta, which is now Malus's law. And you can see what it looks like. It starts at I naught, and then it goes to 0 at 90 degrees as expected, but then it comes back again at 180 degrees, and so on and so forth. Okay. Okay. Then in the last class, I introduced to you also the sign convention, or the way in which we depict the vector diagrams for polarization by reflection. This is another way to polarize light, where if you take a dielectric medium like glass and you shine light on it, and if the light consists, say, exclusively of S-polarized or perpendicular polarized light, where the electric field is perpendicular to the plane of incidence, then this is our orientation of all of the electric fields. So E is always pointing up or out of the plane of this screen, and B has to point along this direction to satisfy the fact that K, E, and B form a right-handed triangle. Okay, and this is called S polarized, or as I said, perpendicular polarized, or TE polarized, etc. All of those. And in this situation, as the way I have depicted it, RS is greater than 0. That's because both of them are pointing out of the screen in the same direction. If RS were lesser than 0, then this electric field vector would be pointing into the board, and that would mean that RS is lesser than 0, and the electric fields are anti-parallel to each other, and that would be depicted, for example, with a cross, to an X, showing the electric field going in. So this here, once I derive the Fresnel coefficients, which I will do in the in that video that I post for you. I don't know what happened to the numbers. They were on the last week's slide, but they got left out here for some reason. The numbers on the X and Y axis. Sorry about that. It was in the slide that I posted last week. So, but this also includes the Fresnel coefficients, which is R perpendicular, or RS as we are calling it, and this is R parallel, or RP as we are calling it. And you can see the what it's defined as is just a ratio of the amplitudes for the reflected light for the perpendicular polarization, and this is the formula for it. Similarly for the parallel, and that's what has been sketched in this plot over here. And I think in the last class, I pointed out to you that there are kind of an interesting angle here, which is called Brewster's angle. And Brewster's angle, it turns out, occurs when the angle of incidence and the angle of transmission make a 90-degree angle with respect to each other. Okay, so and when that happens, the parallel reflection coefficient RP goes to 0. So that means that even if I send an unpolarized light, because RS, remember, is always lesser than 0 and is never vanishing. It grows and grows until it reaches the 90-degree incidence angle. So at this point, the Brewster angle, when theta I plus theta t equals pi over 2, then what happens is that the parallel polarization vanishes, which means if I send an unpolarized light, which consists of equal amounts of S polarized and P polarized light, but like we've talked about, like a fraction, like a half, then what this is saying is that the reflected light will have no parallel polarization. So the P polarized light will vanish, and you'll be left entirely with just S polarized light. So the light coming off of the glass block at Brewster's angle will be entirely S polarized. So this is one way to create a polarizer by just changing the angle of the incidence beam till you hit Brewster's angle. And at that point, theta I plus theta t equals pi over 2. You will get perfect polarization in principle of the reflected light, and the reflected light will be polarized perpendicular to the plane of incidence because it will be purely S polarized. So just to quickly, from that fact that at theta I plus theta t, it's 90 degrees, and there's some physical reason which I won't get into at this point, but let's see if I do this. Stop the share for a second and just point out the consequence of this fact of the Brewster angle, which you should know how to get that formula for the Brewster angle. So notice that theta I plus theta t is equal to 90 degrees or pi over 2 at the Brewster angle. So I'll call that theta IB. So that's the incident angle, which is called the Brewster angle, at which, as I said, the reflected light is entirely S polarized. So we know from the Snell's law that this must be true. And now putting in theta IB on the left-hand side and on the right-hand side, I put in NT sine pi over 2 minus theta IB, the incident angle that corresponds to Brewster's angle or just Brewster's angle. And now this, of course, is just NT cosine of theta IB or theta B. Sometimes I'll just drop the I. It's understood. So we immediately get that tan theta B, Brewster angle, is equal to NT divided by NI. Okay, and so this is the formula that you might have seen in your lab experiment where you calculate the Brewster angle and then compare it to what you got in the measurement, and it comes from this. And okay, the exact physical reason, maybe I'll come back to that, why this is true, why it's at 90 degrees. Of course, one can say it's just from the Fresnel coefficient, but there's also some intuitive picture. We might try to build on that once we have the Fresnel coefficient derivation. So having talked about, I talked about RS, which is the for this situation, and also notice the situation is for ray incident from air to glass, which is we call external reflection. I'll come back to that just a minute. Brewster's angle. Okay, now this is the other situation for p-polarized light. So now what we call p-polarized light is when the electric field is in the plane of incidence. So this is shown over here. So you can see the electric field is in the plane of incidence. And in this situation, the magnetic field is perpendicular to the plane of incidence. Okay, because E and B have to form a right-handed triad. So we see that's the situation. And again, the sign convention here has been chosen to make RP greater than 0, where the convention is that any component that's pointing upward, if I take that to be, say, the y-axis, for example, or something, then that y-axis should be that component along the y-axis for the electric field or for the magnetic field, whichever field you're considering must be positive. That's the positive direction for those vector components. And And therefore, in this situation, again, RP is greater than 0 because electric field, the component along the normal is pointing up, and so is positive. And similarly, for the incident field also is positive. So the ratio between them will be positive. So RP is greater than 0. Okay. And we can also then from that derive this thing that you've seen in your lab, where, for example, if I have an air glass interface and I send in 45-degree polarized light, where the 45-degree polarized light is at an angle of 45 degrees with respect to the vertical, which is what you did in your lab, that it was polarized at 45 degrees. And we call that minus 45 degrees because it's clockwise from the vertical, and counterclockwise angles are usually taken as positive, clockwise angles are taken to be negative. So this is depicted looking from the glass into the beam again. So we always remember our convention in all of polarization when we think about how to depict the polarization state is always to look backward along the beam. We are the observer looking back into the source. And so that incident light is then, if I call this, X and Y or S and P, as is shown here, then E naught over root 2 S plus P, this is exactly the state of the light. So it's got equal components along the S polarization and the P polarization. And now let's say that, for example, like in that first figure I showed you for RS, where RS was lesser than 0 and RP was greater than 0 for angles lesser than the Brewster angle, for example. Okay, that was the first graph that I showed you for the Fresnel coefficient. For angles less than the Brewster angle, RS was lesser than 0, RP was greater than 0. Well, what will happen then is RS, this component, that is the angle, the amplitude of the RS component will be multiplied by RS, right, for the S component. And similarly, the component along the P direction will be multiplied by RP when it's reflected from the glass beam, from the glass interface. So what happens then is, so if I take RS as lesser than 0, now the component along the S axis or S direction has flipped its sign, and the component along the P direction remains the same, except it's different than what it was before. Earlier, they were both equal. Now, RS and RP may not necessarily be equal because it depends on the refractive index of the glass. So now the reflected state of polarization is E naught over root 2 RS S hat plus RP P hat. And you can also see the angle alpha now that it makes with respect to the vertical is going to be positive because it's clockwise, counterclockwise from the vertical. So now this is again depicted looking into the beam. So alpha is now greater than 0. This is how the situation will be. So when you initially start out the experiment, usually you're coming in at an angle which is smaller than the Brewster's angle. So alpha in this situation will be greater than 0. And then as you move towards Brewster angle, eventually you'll get to the point where RP goes to 0 and everything is along RS. And that situation is, of course, when the angle alpha will approach 0 degrees. Okay. So as shown there, alpha becomes 0 when the state of polarization is entirely along the S direction.
Can we express S and P and replace that with a complex plane? And then for when we are expressing the phase and then the intensity, I think that, and then take the real part, I think that will make it, that will be easier. So why do we need this kind of SP system? So instead of the projecting, or do just work in a complex plane?
Why do we need the complex plane?
Can we just rewrite this in a complex plane?
Sure, you can always rewrite anything in the complex plane, but this is like a vector. So for the complex plane, what you're talking about is if there's a phase shift between the components. Yeah. So if there was a phase shift, which I'll come to in a minute, then yes, we may need to worry furthermore about phase shifts between the S and the P component. And then we have to worry about the state of light, which, as I've told you, in general, the state of light may not be linear polarized coming off of the beam. That depends on the phase shift.
Yeah, I guess
of the glass interface.
Yeah, I guess in the complex plane, I think the calculations can be easier.
Okay, maybe. Okay, and that I just took the same coefficients RS and RP that I had plotted on that earlier graph a couple slides ago, and then using this definition of the alpha from this slide, I now replotted that for the using the numbers RS and RP that I have from the Fresnel coefficient, and this is the theoretical prediction for the alpha. So I've just done exactly what just taking numbers and dividing them to get you the alpha, and that gives you this graph, which you must have seen again in your lab experiment. Okay, and you can do all these things too. Just plug the numbers in with Mathematica or something, and you'll get this. That's what I did. Okay, so we want to consider one other situation, which is instead of the light being incident from the air on the glass, which is your lab experiment, you could also have the light incident from glass into air. So we call that internal reflection, right? Remember, we talked about external and internal. External is when the incident medium has lesser refractive index than the medium that it's incident than the other medium. And the other one is in the case like this, where the incident medium, that is the ray, starts in the glass. So that refractive index is greater than the medium that it's going into. So in that case, the Fresnel coefficients look a little different. They look like this. So this is RS and this is RP. So again, RS starts out greater than 0 and RP starts out lesser than 0, just like in the other internal reflection case. But now they curve upward rather than curving downward towards -1. Okay. So here they both curve upward and hit 1, and they hit 1 at an angle which is much lesser than 90 degrees. If you go back a few slides and look at it, in the case of the external reflection, these two amplitude coefficients only, or this reflection coefficient, hit -1, which would be perfect reflection, only at 90-degree incident angle. That's because that's what we call grazing or glancing incidence, when the beam is almost parallel to the interface. So here's the interface, and if you change the angle, so initially the angle is small, almost 0 degrees of incidence, which means it's almost normal to the interface, and then I slowly tilt it until I reach almost 90 degrees. Now I'm coming in almost parallel to the surface to which I am, from which I'm looking at the reflection. The same thing here. We are starting with say small angle of incidence, but here we notice that it goes to 1. The reflection for both the S and the P components goes to 1 at a much smaller angle. This, of course, is the critical angle that we have talked about earlier in ray optics from Snell's law that you can derive, and that's exactly what the Fresnel coefficient says. Notice there's also a Brewster angle here. Okay, this Brewster angle is again the point at which the P polarized component vanishes. So you can also get perfect reflection from, in this case, or perfect polarization in this case, for the beam that's reflected from the interface from glass to air. There will be a point, this angle over here, where this Brewster angle is now RP is equal to 0, and now the reflected beam is entirely S polarized. So same idea, but just the angle is different. In fact, if you look at the angle here and the angle in the previous situation, those two exactly add up to 90 degrees as well, and that's also guaranteed by the Fresnel coefficients. But we won't prove that here. Okay, this is your lab experiment that you did. I won't go into too much detail. This is how you calculate the alpha, which you can see why it is done this way, because alpha is just simply the ratio between that RS and RP from that earlier vector figure that I drew a few slides ago. And so we're just calculating an alpha from this graph. Okay. All right. The last thing I want to talk about, sorry, I put that as review because but I'm only introducing it first here, which is that from the Fresnel coefficients, we can also derive these phase shifts, meaning by phase shift, I simply mean that we talked about, the RS being lesser than 0 or RS being greater than 0. Well, we can obviously have some in-between situations. So here you can see for external reflection, Ni lesser than Nt, which is the air to glass interface, that the S component always has this pi phase shift relative to the P component. Okay. Anyway, this is just coming again from the Fresnel coefficients. So we can see that we have to take this phase shift into account, meaning that the direction of that ES and EP, those two are always opposite to each other, for example, in this situation, until they reach the Brewster angle, at which point they both have the same phase shift, which is that they are in the same direction, negative together. Okay. And similarly, we can have here, so again, RS is lesser than 0. Sorry. one slide earlier, RS lesser than 0, RP greater than 0 up to the Brewster angle, and then after that they both become lesser than 0, and that's what this graph, this phase shift is showing you. So between these, in this angle range, the two of them have opposite phase, and then over here they have the same phase, anti-parallel to the incident beam. Okay. Now for internal reflection, the situation is a little bit more complicated. Again, when we start out, we have that RS is now greater than 0, meaning the phase shift is 0, and RP is lesser than 0, which means the phase shift is pi from that graph that I showed you. But then once there are like two different situations. So you can have the situation where RP basically goes to 0 here at this angle, which is now the Brewster angle, and then at and then we hit the critical angle after which these two both are at some ratio, which is not necessarily always pi or 0. That's just dependent on the ratio of those coefficients that are in that earlier figure. Anyway, we'll come back to this when we have to discuss interference, because when we do interference between two film or different situations, we are taking a phase shift, an extra phase shift that we have to worry about when we do interference between the beam that's reflected from one interface and another interface. So that's why I put these graphs up here, but we'll return to them when we discuss those interference cases. So I just want to ask you a quick question. So I'm just curious to make sure that we are all on the same page with this. So when unpolarized light strikes a glass surface from air at Brewster's angle, which of these is the correct answer? Okay, so no light is reflected. Reflected light is polarized in the plane of incidence. Reflected beam is polarized perpendicular to plane of incident. Reflected beam makes a right angle with the incident beam, and total internal reflection occurs. So if you want, you can talk to your friends, neighbors, and tell me what you're thinking what the answer is. Which of these is the right answer? Yeah.
Yeah, so I think it's oh yeah.
I see. Thoughts? You have thought. Well, there's no gradient. I don't exactly.
I was thinking CFD, but I'm also just like
How about you?
I think C.
Yeah.
How about you over there?
Yes.
C. Okay. You need to work C. Please. Very good. Yes. 3 years.
Yeah.
If you are really looking for to be a group, I'll take you. Right.
actually all things to get this week.
Okay, I'm getting most of you are thinking it's either B and C. So indeed, the answer is C. And the reason for that is that at Brewster angle, the RP, that is the reflection coefficient for the P polarized light, goes to 0, and RS, which is the S polarized light, is still finite here. Okay, So that's one way to think about it. The other way is, as I've said, we argued that at that point the beam and yeah, this one is never true because theta I is always equal to theta r. So it doesn't have to be ever, the sum of them don't always have to add up to 90 degrees for d. So okay, so just remember that the reflected beam is polarized perpendicular to the plane of incidence at Brewster's. Okay, so for the next part, and also for the part dealing with interference, I want to come back to a topic that we have sort of glossed over or not proven mathematically so far, which is the fact that we are always, when we are calculating the intensity or the effect of the electromagnetic wave on detectors, we're always squaring the amplitude, right? You remember we talked about that way back when we first discussed waves, and I said, you take a spherical wave, then the energy in that wave, is going as a square of this amplitude E. And we have referred to it multiple times, even when we talked about polarization, and we will now refer to it as well when we talk about interference, but we've never actually shown this fact. So I just want to quickly show you where this is coming from, where the fact that the intensity or the fact that when we consider what a electromagnetic wave does to, say, a detector like our eye or a CCD camera or like a photographic film, why is the response of those things always driven by the square of this electric field? Okay, the simple answer is, of course, we know that in general, like energy is going to be proportional to the square of the amplitude. Like for a harmonic oscillator, we saw that, and so on, and it's the same idea here. The energy from the of the electromagnetic wave is always wait, what happened here? Some slides. Second here. Drop the slides. It's a copy slides from last week, this week. Someone missed a slide here. Here. Sorry for this. Okay, so to do that, we introduce a new vector, which is called the pointing vector. And the definition of the pointing vector is S, which is equal to 1 over mu naught E cross V. And that is equivalent because 1 over mu naught epsilon naught is simply the velocity of light squared, c squared. We have, or if it's in a medium, then it'll be 1 over mu times epsilon equals v squared, where v is the velocity. So we get that S is also equal to c squared epsilon naught E cross V. The main point being, again, E cross V, the cross product between E and V, is parallel to the direction of the pointing vector, which we know for plane electromagnetic waves, E cross V is also along the K vector, okay, for the wave. And therefore S, which is the pointing vector, is always parallel to this K vector. Okay, and I'll just show you in a minute that this S, this pointing vector, gives us the intensity of the wave. Okay, so in the case of harmonic waves, I substitute in for E and B as usual. E equals E naught with the vector sign cosine k dot r minus omega t. B equals B naught cosine k dot r minus omega t. So when I substitute all that in here, we get c squared epsilon naught E naught cross B naught, right? So that's the E naught and B naught are the polarization vectors for the light times this cosine squared, K dot R minus omega T. Okay. And if I now go back here, which is what I was trying to get to. So now we take that expression for that E naught cross B naught, and I substitute in, I'm going to simplify that expression to a specific simple case, okay? Because we just want to understand the simplest case, and the result turns out to be then generalizable to the more complicated cases. So we'll take the case again, as usual, of an electromagnetic wave along the Z direction. We already showed when we talked about electromagnetic waves, then that is E is along the X direction, B will be along the Y direction, and furthermore, the amplitude of B will be 1 over the velocity times E. Remember, we said that that's one of the reasons why the magnetic field is usually not considered when we think about the response of many detectors, because the electric field is usually much bigger than the magnetic field in terms of numbers. Okay, so I take this B equals 1 over C times anyway, I take this B equals 1 over C E, and then I substitute that into the expression for the pointing vector. So I will get Z times and then I put in that E is equal to X hat and B is equal to Y hat, B naught cosine KZ minus omega T. When I substitute all that in, I get that the pointing vector is now along the Z direction, C, and then it's given by this expression C epsilon naught E naught squared cosine squared KZ minus omega T. And furthermore, we're going to now make a clear physical approximation, which has nothing to do with the definition of the pointing vector, but has to do with the fact that at optical frequencies, omega, the frequency of light, is 2 pi times 10 to the 14. Okay, so that's a very large frequency, approximately, right? I mean, even if you take 400 nanometer light versus 800 nanometer light, it'll just change the number in front of us. It'll just be that factor of 10 to the 14 is still there. Okay, so most optical detectors cannot follow the field directly, like they can't respond directly because it's such a large frequency. Okay, instead they average the field over some time t. Okay, and that time t is usually much larger than the period of the oscillation. Even your fastest cameras, photon detectors, etc., typically are going to average over like microsecond time scale. Okay, so a microsecond, and this is 10 to the 14, which is like 10 femtoseconds. That's the time period of an electromagnetic wave for visible wavelengths. Now, microwaves are a lot shorter than that, or rather longer in time period than that, because microwaves are like about 10 to the 9 hertz, which means that their typical wave time scale is like a nanosecond. So you can build detectors that directly follow the microwave field. Okay, and so you'll see detectors where you can actually observe the oscillation of the microwave electric field or magnetic field, etc. But for like optical frequencies, it's very hard to build a detector. You know, in fact, we have to use light itself to sort of measure these kind of things. But most regular detectors, like I mentioned, are going to average on typically like a microsecond or even nanosecond. The time scale, well, that's still much, much longer than the period of the electric field, which is like 10 femtoseconds. Okay. So when you want to average something, well, you take the sum of it over various time points and then divide by the total time, right? That's what you do, which is in the uniform or continuous limit, that's just an integral. You just take the sum over a bunch of like time points and then divide by the total number of time. And that's exactly what this integral is. So this is the time average pointing vector now, which is just integral 0 to t s dt, which is the magnitude of s. Okay. And this quantity is what we call the intensity or irradiance. And it has units watts per meter squared, which you can verify. So furthermore, we usually can pick this time period t to be some large and multiple, okay, of the time period of the electric field. T equals some integer n, which is very large, times 2 pi divided by omega. Because t is so large, I can as well pick it to be, you know, some multiple of the period because the fields are harmonic. So if I know the integral over one period, I can extend it to any number of periods as well. Okay. And all these can be proven more mathematically. I'm not going into it. So here, all we want to know now is remember that the time dependence is in this quantity cosine squared kz minus omega t. So I just need to know what is the time average, which is defined by this integral 1 over t integral 0 to t of this cosine squared function. Okay. Well, I won't go through the math here. It's quite straightforward to do. Just put kz minus omega t as some constant or not constant, some other variable, and then do the integral over cosine squared, and you get that it's exactly 1/2. Okay, when t is some multiple of the time period. Okay, so this allows us to now write the time average Poynting vector as substituting. Oops, why did that run away? Sorry, substituting this as half. That's half times c epsilon naught e naught squared, which is what I promised that I would show you. Okay, that formula got taken off. I had to fix that animation, but it's that before it disappears. Okay. Okay. So there is another way to think about this formula for the Poynting vector, which is in terms of the energy density. Okay. So again, we remember that our picture is that the irradiance or the intensity is the amount of power of the electromagnetic wave that is crossing some cross section A. Okay, remember its unit is watt per meter squared, so it has that physical intuition that it's the power crossing some unit area A in some time period t, delta t here, for example. Okay, well, it's power, so it's just per unit time as well, energy per unit time. Well, we can derive that also from knowing the energy density that is in an electromagnetic wave. Again, these are expressions that we can get from just looking at the electromagnetic wave theory or electric fields, etc. We know that the energy density in an electric field is half epsilon naught e squared. Similarly, the electric energy density in a magnetic field is 1/2 mu naught b squared, and for an electromagnetic wave, we substitute b equals e over the velocity c. Okay, so we have the expression for ub and ue, and these are equal to each other because I just substitute for c as mu naught epsilon naught, square root mu naught epsilon naught, and I'll find them to be equal to each other. So the total energy in the wave, U, is, or energy density in an electromagnetic wave, that is energy per unit volume, is 2 times this UE, which is half epsilon naught E squared. Okay. So knowing that and knowing this, that we have this much energy in a box, and let that box have a length of C times delta T. Why do I choose that? That means in a time delta T, all of the energy that is, or all of the electromagnetic wave that starts over here will cross the plane, which is A, depicted by A in the time delta T. So, or if I think of it as photons, if there are any photons starting out at this point over here, in a time delta T, they'll cross this box and go past this plane A, which is where I want to calculate the intensity or the flux of photons. Okay.
So is this equivalent to like the pure continuity, like a continuity equation for the flow?
I guess so, but I mean, really, I'm just making a physical argument for that expression that we just saw. So the earlier expression for the intensity, I'm trying to motivate it by just thinking about the total energy that is crossing a plane A in a time delta T, and how we can get that from just the energy density of the wave. Okay, so I'll just quickly mute this and explain that in a minute. So we have the expression U for the intensity in the wave, which I said is just the sum of the magnetic and the electric field energy densities. So that is just this, and we also and we saw that these two are equal to each other. So that gives me, this is 2 times UE, which is the energy density in the electric field alone. Then if I take a box, of size of draw a very good box. Here's my box with a plane of cross section A, and any electromagnetic field that is in this box to the left of this and the length of this box is C times delta T or V times delta T, where V is the velocity of the wave. Then anything that's in this box will cross this plane A. So the total power crossing the plane A equals U, the energy, times the length of the box, because it's energy density, which is energy per unit volume. So UAV delta T is the total energy that's in this box, and that will all cross the plane A in the time delta T. So that's the power that's crossing that plane A. Okay, and the intensity or irradiance is equal to the power divided by the area. So again, we get UA V delta T divided by A delta T. So we just simply get U times V. Okay. So then going back to our expression for going back to our expression for the electric field, we get 2 times UE, which is this expression over here, 2 times epsilon naught, half epsilon naught E squared. So that's just going to give me epsilon naught E squared times now the expression for the energy, that's V. And of course, E is now again has that cosine squared, kz minus omega t. So I have to time average it, and then I get back the half. So this is another alternate way without the without just knowing about the point emitter to find the intensity in the wave, and it gives you the same expression. Okay, so to conclude our sort of discussion of these reflection coefficients, we've been talking about the reflection coefficient, which is just the ratio between the electric field which is reflected and the electric field that's incident, right? That's what we've been using so far. But as I said, we are mostly interested in a lot of cases in the intensity of the beam that's coming off of this interface. And the problem with that is that they are not the same. Okay, so it's not always. It looks like the intensity is just epsilon naught V over 2 times E naught squared. So if I just take the square of the reflection coefficients, I should get the intensity of the reflected beam. That's not quite true because we have the expression. We have this velocity in there. And the velocity in air is different than the velocity in the medium. So that V is going to affect the intensity of the beam in one medium relative to another medium. The other thing that changes the intensity or the power, the reflection coefficients, which are the power reflection and power transmission coefficients compared to the amplitude coefficient, is the fact that that there's this geometrical factor, meaning if I have a beam of cross-section area AI that's incident on this cross-section A, then A and AI are in the ratio given by these angles, theta. Okay. Similarly, A and AT are in the ratio given by their angles or cosine of their angles, theta T. Okay. So those two facts make a difference between the power coefficient. So you can't just take the reflection coefficient and square it. You have to worry about the fact that maybe the velocity is different, as well as the fact that maybe these angles, if they are different. For example, mainly this has an effect on the transmission coefficient, because the transmission is usually in a medium that has different velocity or different refractive index, and it has a different angle with respect to the interface than the incident and the reflected beams. Okay. So to carry out the calculation, what we do is we look at the total incident power, and that has to be equal by conservation of energy to the reflected power plus the transmitted power. And so we know that the incident power is just the intensity times the area. This is the reflected intensity times the reflected area, and this is the transmitted intensity times the transmitted area. And now I substitute using the geometry of this situation that this is A cosine theta I, this is A cosine theta R, theta I and theta R are equal, so this is the same. But this one is different. A cosine theta T is not the same as theta I and theta R. Okay, so now substituting in from this expression for V being different, as well as the medium having a different refractive index, which means it has a different dielectric constant. So putting all that in, we get this expression for the ratio between the amplitude coefficients or the amplitudes of the reflected beam and the transmitted beam, as well as the incident electric field. Okay, so we can identify we can identify all of that. So if I now divide by E naught squared, this part here is the reflection coefficient. So that's R squared. Okay. We call that as the reflectance or the power reflection coefficient. Okay, so that's R, which is simply R squared. So that part is okay. We can just take the Fresnel coefficient for the reflected beam and just simply square it. But the transmittance, meaning the part that's transmitted through the medium, is not necessarily simply small t squared, where t is the Fresnel transmission coefficient. We have to now multiply by this factor, which is n times cosine theta t by cosine theta I. For normal incidence, we can even take theta t and theta I to be equal to each other, almost equal to each other, but then we still have the refractive index n, which is multiplying this coefficient for the transmission. So this is the true relationship between the reflection coefficient and the transmission coefficient, and the Fresnel reflection and the Fresnel transmission coefficients, between the power and the amplitude coefficients. Okay, so one of the nice things about having all of this stuff is that there are ways in which you can just understand this more intuitively by playing with the amplitudes of the refractive indices, the incident angles, and so on. So I'm just putting up here an applet that is quite useful if you want to play with this to understand how the polarization changes as you change the angle and the various incident and the incident refractive index and the transmitted medium refractive index and so on. So this is the link to that. I encourage you to try it out on your own. Okay, so I'll pause here. I guess we'll have to talk about interference in the next class, and also a little bit still cleaning up this polarization part. We'll talk about interference and polarization in the next class. Thank you.